Okay, so I'm going to be telling you today about the what and the why of framed mapping class groups. And just to advertise my collaborators here, I'll be talking about projects that have been carried out with Aaron Calderon and with Pablo Portilla Cuadrado. So part one of this talk is the what. That is, I'm going to explain what a frame mapping class group is and what I've been able to show about them. So the starting point for all of this, let's just remember what a framing is. So a framing in the language of differential topology is a trivialization of the tangent bundle of your manifold here. And in less abstract terms, this can be accomplished by specifying n everywhere linearly independent vector fields on your manifold, if your manifold is an n manifold. So for surfaces, this turns out to be particularly easy to describe. If you have a non-closed surface, so you want something with at least one boundary component or puncture, then regardless of the Euler characteristic, you can construct a non-vanishing vector field. So if the manifold is also orientable, then you don't even need to specify two different linearly independent vector fields. You just need to specify one, and then you get the second one for free. By using the orientation, you can sort of differentiate between going 90 degrees clockwise and 90 degrees counterclockwise. And so the upshot of this is that every non-closed orientable surface is frameable. And so what I've shown here is just sort of a running example that we'll be looking at. This is a picture of a framed surface. And what I've illustrated is that the notion of horizontal on this picture here, with all of these arrows here, gives us a non-vanishing vector field. The only point at which this rule sort of fails to give you something well-defined is at the red point, which is a single point on the surface that sort of corresponds to the cone angle point here. As typical in sort of problems involving the mapping class group, the specific framing is not really we don't need to carry all of that data around. And so for the most part, what we're interested in here is just the isotopy class of the framing. So this brings us right away on slide 2 to the definition of a framed mapping class group. If you're watching this video, then you probably don't need a reminder on what the mapping class group itself is, but just to be safe, the mapping class group, our notation for this is mod sigma. This is the group of components of the orientation preserving diffeomorphisms of the surface. So this is just diffeomorphisms up to isotopy. And the mapping class group acts in a very natural way on isotopy classes of framings. If you like, the mapping class group acts on isotopy classes of vector fields. Simply pick a representative diffeomorphism and then let that act on the vector field and then take the isotopy class. And so this gives us an action on the set of framings via this correspondence between vector fields and framings. And so here's our definition of the frame mapping class group. Let's take phi to be a framing of the surface, and really we mean an isotopy class of this. And the framed mapping class group, which we write mod sigma phi, this is just the stabilizer under this group action. So here's our frame mapping class group. And what do we know about this? The first place in the literature that I've seen the frame mapping class group is in a paper of Oscar Randall Williams. And what he was able to show about this was he was able to prove a homological stability result for this. And one of the sort of outputs of this is a sort of interesting fact, gives you the abelianization of the frame mapping class group. And he shows that it's finite cyclic. But beyond this computation, frame mapping class groups really haven't been explored very much. So I'm going to tell you what Aaron and I have proved about frame mapping class groups. And here it is. So for any surface of genus at least 5, and you take any framing, there is an explicit finite generating set for the frame mapping class group. And it's extremely concrete. It just consists of Dane twists. And you're probably wondering about the asterisk I've put on this theorem statement. It's not just that there's one explicit finite generating set. In fact, we give a criterion that's very, very general. And in the second part of the talk, I'll sort of walk through exactly how this criterion works and how you can apply it in some different contexts. But the point is that we give a very flexible criterion for a set of twists to generate the stabilizer of a framing. As I said, a precise statement of this will be given in part 2 of the talk. For right now, I just want to show you some pictures. So here's one picture of a framed mapping class group. It's the kind of standard picture of a surface, and I've drawn a bunch of Dane twists here. And one thing to comment about at this point is, I haven't specified what the framing is in drawing this picture. The curves that I've drawn here are stabilizers for the particular isotopy class of framing implicitly specified by the condition that all of the twists that I've drawn are in the group. For another more exotic example, let's look at this picture. In this picture, we're going to sort of walk through this example in detail in part 2 of the talk. This is a picture that sort of arises out of singularity theory. But so what you can see in this picture here is that this surface here is the Seifert surface for some kind of a link. In fact, it's a knot. And so this is kind of the typical setting, actually, in which a framed surface is going to be handed to you, is that it doesn't sort of come to you as one of these sort of nice kind of standard, breadstick style surfaces. It's actually something much more involved. A slogan that I want to advocate for is that this theorem is coordinate free, in the sense that, like, the Humphreys generating set for the standard mapping class group requires a specific identification, the sort of identification of your surface with the top picture. And then it says, this specific set of curves is a generating set. Whereas our theorem is coordinate free. It gives a criterion sort of based on the combinatorics of the way that these curves intersect each other that kind of can be applied equally easily to the Seifert surface picture. So I want to make a couple of comments about this theorem right off the bat. And the first one is to observe the fact that the frame mapping class group is infinite index inside the ambient mapping class group. This is not obvious, but it's not especially deep. It's just a consequence of the fact that the orbit of a given framing has infinitely many elements in it. And what our theorem says is that there's a finite generating set for these. And this is fairly surprising. And it also follows a theme that I want to advertise in the study of mapping class groups that I would like to understand better. And this is that stabilizers of geometric structures, like framings, tend to have unusually strong finiteness properties. So let me just sort of spell out a couple of other instances of this principle. And the first one is very basic, just stabilizers of curves and subsurfaces. One of the basic things you learn when learning about mapping class groups is that the stabilizers of subsurfaces can be identified with the mapping class groups of the complementary surfaces. And so these are therefore finitely generated because the mapping class groups themselves are, but they're usually infinite index. So this is an attribution here. We'll see some attributions to other theorems in a second here. So the Torelli group is also kind of a stabilizer of a geometric structure. It's the stabilizer of a marking and homology. And this, of course, is the famous theorem of Dennis-Johnson. More recently, the full Johnson filtration, if you happen to know what that is, was also shown to be finitely generated. And this was, I think, even more surprising than finite generation in the Torelli group. The relevant names here are Church, Ershov, Hay, and Putnam. So another kind of aspect of this that I would really like to understand is the theory of presentations of the frame mapping class group. I'd like to understand, if not a presentation, then at least some sort of geometrically meaningful and hopefully kind of a complete set of geometrically meaningful relations in the frame mapping class group. And there would be some real applications to the same sorts of problems that we're going to be studying in this talk. So that was part one. That's kind of the what of frame mapping class groups. And the upshot of this is that now we have a way of specifying a finite set of generators for this. And so in this part of the talk, I'm going to go through and talk about why we're interested in answering this question. So the key word for this whole part of the talk is monodromy. And the context here, monodromy arises when you're studying families of Riemann surfaces. And families of Riemann surfaces, they're everywhere you look in mathematics. The idea is simply that, when you have a single surface, you can vary all sorts of different algebraic or geometric structures on it and get families of surfaces this way. So, if you're doing geometry, you might find yourself in a situation where you're studying a family of different hyperbolic metrics on a surface. If you're doing algebraic geometry, you'll be studying different algebraic curves, and they're varying, according to some other algebraically varying parameters. And these sorts of things are sort of often at the heart of a lot of interesting math problems. And when you have a family of Riemann surfaces, if you want to understand its topology, or if you want to understand finer questions about the geometry or the algebraic structure of this family, the first, and in many cases, the last line of attack is this invariant called the monodromy. So what is the monodromy of a family of surfaces? So to set this up, I'll sort of formulate this in a topological way. We have a base space B, which is, the space of parameters in our family. And sigma is our surface, it's the fiber. And so given such an object, we have a homomorphism from the fundamental group of the base space into the mapping class group of the fiber. And this is what the monodromy is. And what this does is it measures how the fibers twist as you transport them around loops in the base space. And given a family of Riemann surfaces, the most basic question you can ask, which encodes all of the topology and everything that I've said above, is you need to compute this monodromy representation. And so this is sort of the first primary application of the theory of frame mapping class groups, is that it's going to tell us the answer to monodromy problems for some very important families of Riemann surfaces. So you'll notice the ellipsis on the title of the previous slide, monodromy in the presence of framing. So I'm talking here now about what we can understand about the monodromy representation of a family of surfaces when it comes equipped with some additional structure. So what sorts of additional structure are we talking about? We're talking about framings. And so the setting here is when we're looking at a family of surfaces where each fiber is not just a Riemann surface, but it's a Riemann surface together with a choice of framing. And these sorts of things turn out to be surprisingly common. Way back at the beginning of the talk, I said a little bit about translation surfaces, and this is one of our primary applications here. The point is that when you have the structure of a translation surface, the forward horizontal direction is a canonical framing, and as you move around in the space of translation surfaces, the framings move around too. And so this gives you some extra structure on your monodromy, which is why we're interested in studying the frame mapping class group at all. So the observation is that if every fiber comes with a canonical framing, then the monodromy doesn't just live in the mapping class group, it lives in the stabilizer of the particular framing that exists fiber by fiber. So here's the key observation. If you have a framing of each fiber, your monodromy is valued not just in the mapping class group, but in the framed mapping class group. So having proved our main theorem, namely giving a criterion for gain twists to generate the frame mapping class group, this is now the tool that we need to show when equality can hold. So for the remainder of this talk, I'm going to go through and describe sort of the two applications that we've used this for so far. And so the first one is translation surfaces. So here's a quick primer on translation surfaces. These come to you in sort of two different ways. In algebraic geometry, a translation surface is described to you as a pair x omega, where x is a Riemann surface and omega is a holomorphic one form on the Riemann surface. So for example, this equation x cubed plus y to the fourth describes an affine Riemann surface. You can projectivize this by embedding it in P2 and taking the closure. In this particular affine coordinate chart that I've written down, a holomorphic one form might be something like dx over y cubed. Translation surfaces also appear in kind of geometric geometry as opposed to algebraic geometry, and it comes with a totally different looking definition. And so to a geometric geometer, a translation surface is just a surface with an atlas of charts to the complex numbers, where the transition functions are given by translations, just z goes to z plus c. And so here's another picture that's sort of in the same style of the picture I showed on the first or second slide of a translation surface. Here you can sort of see that I have three different colors, and within each color there's exactly one pair of parallel sides, and all of those are identified by translations. So how do you pass between this? How do you take this funky polygon picture and turn it into an algebraic equation? You recognize that this thing sits inside the plane. namely the complex plane. And on the complex plane, there's a holomorphic one form called dz. And so by sort of equipping this with dz, which moreover is invariant under the coordinate changes z goes to z plus c, you can arrive at the setting of a Riemann surface with a holomorphic one form. To go back the other way, if you have an equation with a Riemann surface with a one form and you want to draw a polygon, you kind of, instead of differentiating something, you integrate something, you take the one form and you use it as a method to get a map into C by integrating. And the upshot of this is that these are the same thing. So if you're interested in studying the family of translation surfaces, these get packaged together in sort of moduli spaces of translation surfaces, and these things are called strata. So a given stratum parametrizes all of the translation surfaces of the same geometric type. And what I mean by geometric type is the following. So every holomorphic one form, every differential has exactly 2g minus 2 zeros counted with the appropriate multiplicity. And it's the particular multiplicities that specify which stratum you live in. From the point of view of geometry, I should remark, the zeros of the one form are the cone points of the associated flat metric. So what you do to build a stratum is you fix a partition of 2g minus 2, and that's going to tell you how you want to assign multiplicity to the zeros. So you pick this partition kappa and you say, I want there to be exactly n zeros, and I want to assign multiplicity kappa 1 to the first zero, multiplicity kappa 2 to the second, so on and so forth. And having specified this, you get a stratum, this space h omega kappa, and this is the set of all translation surfaces, either from the geometric point of view with the cone angle set given by kappa, or with the zeros of the differential being specified by the partition kappa of 2g minus 2. So a stratum parameterizes a family of Riemann surfaces. It's sort of the universal family of translation surfaces with differentials of zeros specified by kappa. And so we want to understand the monodromy of this family. And the first thing to understand about it is that when you have a holomorphic one form, it gives your translation surface a framing. And so given the fact that any given stratum is a family not just of Riemann surfaces, but of Riemann surfaces equipped with a framing, Aaron and I can apply our theorem to tell you what the monodromy of any given stratum is. And so precisely for genus at least 5 and pick a partition of 2g minus 2, one thing I didn't mention before is that strata are not always connected, but they always have finitely many components, and in fact, always at most 3. And the generic situation is that these strata are what we call non-hyperelliptic. In the hyperelliptic case, sort of the monodromy and indeed sort of the global topology of these are easier to understand. So in the sort of generic case of a non-hyperelliptic stratum component, we tell you that the monodromy preserves the framing, but rather it surjects onto the frame mapping class group. So the slogan is that the monodromy is as big as possible, given the sort of evident topological constraint of it needing to live in the frame mapping class group. The second application that I want to talk about is the stuff I did with Pablo, and this is an application to sort of a different topological problem, plane curve singularities. So I want to very quickly just kind of summarize the theory of singularities. So what is a plane curve singularity? Technically it's a germ, but I'm going to ignore this. So just pick a map from C squared to C, holomorphic, say even it's polynomial, and typically you sort of renormalize things so that it sends the origin to the origin. But it's singular when both partial derivatives vanish at the origin. So for instance, it might be something like x cubed plus y to the 4th. This satisfies this. To get a family of Riemann surfaces out of this, it's very simple. You simply look at the nearby smooth level surfaces. So for instance, if you look at the solutions to x cubed plus y to the 4th equals t for small t, these are all going to be smooth Riemann surfaces by something like the implicit function theorem. The language for this, we call these the Milnor fibers. And like in translation surfaces, you want to study some sort of moduli space or the universal family of translation surfaces. Likewise, in singularity theory, you want some sort of moduli space for the kind of the universal Milnor fiber. And these are called versal deformation spaces here. And so these are easy to set up. And they sort of follow a basic theme in singularity theory, which is if you want to study a complicated singularity, you take a perturbation to deform your singularity to some sort of compound of simpler singularity. And kind of taking this as a guiding principle, you can use this to construct a universal deformation space relative to some notion of universality, which I'm not going to define. And the nice thing about this is that it's finite dimensional. And the language for this is, we call this the versal deformation space. And the notation is it's VF if F is our singularity. And I just want to emphasize that it's a finite dimensional complex vector space. So just to explain that these really are quite concrete, for this example, x cubed plus y to the fourth, the versal deformation space has a nice structure to it. It's sort of the set of all lower order perturbations of x cubed plus y to the fourth. So if you sort of parse the string here, you see that we're just adding on terms where x has degree at most 1 and y has degree at most 2. And this sort of follows a kind of general pattern for how to construct the sort of universal lower order perturbations, which you can look up in a text in singularity theory. So if you choose lambda, that is the vector of coefficients in this perturbation, say unwisely, then you're going to get another singular Riemann surface. You know, for lambda equals 0 on the nose, you're just parametrizing x cubed plus y to the fourth, which is definitely singular. And for other ones, maybe you get some more mild singularities. And so to account for this, we describe the discriminant set as just the set of parameters for which the associated level surface is singular. And once we've deleted this discriminant, we have a nice family of smooth Riemann surfaces. So over this discriminant complement, we have the family now of smooth Riemann surfaces where the fiber over lambda is the level set f lambda inverse of 0. And so this is our universal family of surfaces attached to a plane curve singularity. To bring this back around to the theme of framed surfaces, I want to make a simple but very powerful observation, which is that plane curve singularities, Milnor fibers, come equipped with framings. You can write them down very explicitly. If you want to write down a one form, you do the same construction that I did for x cubed plus y to the fourth equals 1. Dx over the y partial derivative is this general recipe for building a one form that is by, its very nature holomorphic and is also non-vanishing on the associated fiber. So the upshot of this, I should say, these are all sort of affine curves. It's non-vanishing everywhere on this particular affine slice, and it picks up zeros in a controlled way at infinity. And so the upshot of this is that using this one form, Milnor fibers of plane curve singularities carry canonical structures as translation surfaces. And therefore, in particular, the monodromy preserves the framing. And so now the question is, what is the monodromy attached to a plane curve singularity? And this is what Pablo and I answered. So here, for any isolated plane curve singularity, and again, we need genus at least 5 because of sort of the foundational work on frame mapping class groups. By the way, isolated plane curve singularity simply means that the critical point where the fx and fy, the partial derivatives, vanish, just vanishes at the single point at the origin and not on some sort of, one-dimensional set. So for an isolated plane curve singularity that is not extremely special, and for the experts in singularity theory, there's exactly 2 classes of singularities for which this theorem does not apply. These are of type A or type D, and this is sort of exactly the hyperelliptic setting. And I should say that this is sort of useful not just for the kind of, intrinsic problem of understanding the monodromy, but a lot of what you're interested in singularity theory and sort of adjacent areas in symplectic geometry is understanding vanishing cycles, which are kind of the bread and butter of singularity theory. And a corollary of this theorem here is telling us what the set of vanishing cycles associated to any isolated plane curve singularity is.